Now, welcome to my YouTube channel. I would like us to talk briefly on this topic, velocity time graph. Now, before we move on, I would like us to introduce us to this concept, velocity time graph. This graph can be plotted using the actual graph paper or also just randomly or with a rough sketch on the board or anywhere you want to be plotting the graph. But the main concept, the main thing that we need is to understand the concept of velocity time graph. Now let's see how we can easily solve this problem of velocity time graph. So I will be doing a brief introduction first of the velocity time graph. The things you need to understand about the velocity time graph is that the graph that is used to plot or that is used to explain the activities that goes on in a rectilinear acceleration or deceleration. What I mean is this: when an object is moving in a straight line, that's what we mean by rectilinear. So when we want to explain the activities that goes on in a rectilinear acceleration or deceleration, deceleration is the opposite of acceleration, we use what we call a velocity time graph, because we all know that acceleration or deceleration is a change of velocity with respect to time. Let's see the further things that we need to understand for us to be able to plot the graph on this. Now, what we need to understand is when an object is moving, it can also, when it's moving, with a velocity, it can also move in three forms. And those three forms has diagrams to represent them. The first form is this. A. When it is moving uniformly or with a constant velocity, when it's moving uniformly with a constant velocity, it is drawn like this. That means the velocity is neither increasing nor decreasing, it's just constant. So we have that, and V is here, mx is the unit, we always place it there. And the time is x. But when it is moving with a decreasing velocity, all I mean is that the velocity is decreasing with respect to time, we draw it like this. The same thing here, we have our velocity, mx, and our time as x, but it will not be drawn like this. The line here shows that the velocity is decreasing with respect to time. And furthermore, we now have the final one when the velocity is increasing. You see, it's accelerating with respect to time. We draw it like this. So we have our v, mx, and our time is x. So when you fully absorb these three concepts, you understand these three things well, and you know which one to use per time when they give you a particular phrase or sentence or anything that has to do with velocity time graph. When they give you any question and they say something, you know which one to apply, then you'll be able to solve the velocity time graph very, very easily. So we'll be looking at some examples on how to use this to solve. You can combine this diagram and you can put it together while solving a particular question. You might say it is moving uniformly, later it now change and started decelerating or started accelerating. So it depends on what we are given. So let's see an example. So here we are with an example. Here we are with an example on Waec 1991. So how are we going to be solving this? We have that the body was moving with uniform acceleration. A has 2 points, 5 and 15, and 20 and 60 on a velocity time graph of its motion. Calculate A. So how are we going to be doing this? With the idea that we learned about in our previous explanation, we will be drawing a graph like this, is free-hand sketch graph, and here is our velocity, and here is our time, because it's a velocity time graph. But from mathematics, we discover that whenever we draw a graph, here used to be our y-axis, and here is our x-axis. But take note, in physics, we don't write this y-axis and x-axis, we just maintain this velocity and time. So here we have what we have. So According to maths, here is supposed to be x1, y1, and here is x2, y2. But for our physics sake now, we won't be using that. So where there is x should be t, because t is in the x-axis. So it's t1 for x and v1, t2 and v2. So on the velocity side now, we have our v1 to be 15. So 15 will come first, then followed by 60. So 60 will come second. And for t, we have 5 first and 20 to come later. So now how do we draw this? Since they said it was moving with uniform acceleration, and I told us that acceleration goes like this. So we started somewhere here, where these two met, and it accelerated to where this one will meet this one. So this is the diagram. So you see very clearly, uniform acceleration according to the diagram, it goes like this. So, and it started from 15 at the time 5 and moved up to 60 as velocity at the time 20. So this is it for the diagram. So they said to calculate the acceleration. Now, how do we calculate the acceleration? We know that the formula for acceleration is change in velocity v2 minus v1 over time. Time. When we talk about time, it means the time that is taken for that velocity to change. And if we look at it, the time that was taken for the velocity to change was from 5 to 20. So what is in between them? 15. So, but if they are to give you normal questions, they will normally give you that the thing was the body change the velocity from 15 to 60 within 15 minutes. But since they give us the first time now, and they give us another time, we'll just change the formula to A equals to V2 minus V1 all over T2 minus T1, because they're giving us 2 time. So here we have, what is our V2? Our V2 is 60 minus 15, and our T1, T2, 20 minus 5. So we have here to be 45 all over this minus this is 15. So dividing both of them now, we have 3. So, and as the resistance is acceleration, it will be in meter per second square. So this is very, very easy for the Waec 1991. Let's take another example. You want to see how you can solve another example, example 2 of Waec. The Waec 1990 question. So now, how can we solve this? They said a particle can be body moving in a straight line with uniform retardation or deceleration has a velocity of 40 meters per second at P, 20 at Q, and comes to rest at R, where QR, the distance is 50 meters. They say find the distance between P and Q, time taken to cover P, Q, and time taken to cover P, R. Let's see with the knowledge we got from the previous lectures on how to solve this. Now let's draw our graph as usual. So here we have velocity, meter per second. Then time in seconds. So they said it was moving with a uniform velocity, a retardation, and has a velocity of 40. So it means 40 was here. 40. Then at point, that's at point what? 40 was at point P. It is 40 at point P. And then at point Q, it was 20. So 20 somewhere here. And comes to rest at point R. So if I want to draw it, says it was retarded. That means it will come down like this, instead of like this. From here, it comes down like this. Or let me make it wider so that you can see space to do more stuff. So it comes to rest. So point P, and here will be point Q. Yes, point Q. Q, and finally point R is here. So we can see what we have, the diagram we have, it was retarded. So now we can also trace something like this down for emphasis. So for to draw it here, we have T1, the first time for it to move from here to here, it is T1. Then for it to move from here to rest, it is now T2. So T1 and T2. Now, how can we solve for the distance of PQ now? If we look at this, the best way, easiest way for you to understand this as a physics student and also a math student is if you have an idea of solving the area of shape in math, you can easily solve this because the area of any of the shape gives yield to the distance covered. So if you get the area of the shape, that means the distance covered from that place to the other place that gave you that shape is actually the distance. So now let's see what we have. So we should find the distance from P to Q. So from P to Q is from here all the way to here and here. So we'll have something like this. If I want to draw it, then we'll have something like this. We'll have something like this. So look at it from here to Q. So this is the shape it will give us. So we can write P here, Q here. So and it was done within T1. So it was done within T1. So if we look at this shape now, this shape looks like a very conversant shape, and that shape is a trapezium. So what is the formula for solving a trapezium? You can say the area of this right angle and the area of the square together. That gives you that. So for us to solve the distance between PQ, we'll have the area of the right angle triangle, which is half base times height. But now we're not talking about base and height, we're talking about half the base, the T1. So half T1 times what is our height? Our height is here. Half base times height. Our height is from here to here, which is 40. Look at it, half base times from here to here, which is what? Actually 20, not 40. So 20 is from here to here and 20 from here to 0. So that's it. So from here to here is 20, from here to here is 20 to make it 40. So here to here should be 20. So now we have 20. So half base times height. Or I can put V1 so that we'll understand it. Later we'll use it to solve. So half T1 times V1 plus the rectangle, which is length times breadth or height times breadth. So have V, okay? Here should be V2. So here is V2. Because it's from here to here, so it's V2. So here you have the V1, half here times T1. So this is what we have. So the T remains the same in both cases, but the V changes because this upper V is V2 and this lower V is V1. So let's put it into what we have. So half, what is our T1? We don't know, times what is our V2? We have 20. But the velocity is, the decrease in the velocity was the same in the two cases. Move from 40 to 20, which is 20 movement. Then from 20 to 0, which is T20 movement. Making 40. So plus here, we have V1. So what is our V1? Is T20 times T1. So here, half of this should give you 10. So it will now be 10 T1 plus 20 T1, which will give you 30 T1. So this is the movement now. You can write meters if you want to, but it is not the final answer though. We'll still come back to it. Now let's move to the second, which is time taken to cover PQ. Time taken to cover PQ. First, what we should understand first is that in a uniform deceleration or acceleration, the object changes velocity at the same time interval no matter how small the time interval may be. So, and since it's covered in uniform, that uniform now will show you that you should explain to you why the movement, the first movement from 40 to 20 and from 20 to 0 was the same. So since it's moving uniformly, the time also taking, the time it will take, that is from this 0 to T1 is the same with from that T1 to T2. So T1 and T2 they are equal because of that concept of uniform deceleration or acceleration. So we have that T1 is equal to T2. So now what do we need to find T2? When we find T2, we will equal it to T1 until we get 42 is T1. So let's move on. So we know that since QR is, or let me just move on, writing it here. Since QR is 50 meters. So, and we also know that for us to find QR, it is from here to here. And the area of that shape of QR, which is a shape like this, let me draw it somewhere, a shape like this, like onto a right angle triangle. We also find the distance of this shape is simply the area, as I taught us earlier on. So T2, since this is this, therefore the distance of this will be half base. The base now is T2. Half T2 times V1. That's the first small space here. Half T2 times V1 is the first V, which is this. So we now have here 50 is equal to half of T2 times what is our V1? 20. So 2 here, 2 here to give you 10. So what we have is 50 equals to 10. 50 is equals to 10 T2. So therefore T2 will be equals to 0 cancel 0. T2 will be 5 seconds. So 50 is equals to 10 T2. So T2 is 5. So since T1 is equal to T2, thus also T1 is equal to 5 seconds. So you see how we got that now, just quite very, very interesting. So we now want to find what is our P, time taken to cover PR. So the time taken to cover PR is from here all the way to 0. So what does it mean? It is simply T total. You can write it T total. That is the total time taken, which will be T1 plus T2, which will give you 5 plus 5. And finally it will be 10 seconds. So that's all. We have gotten that. But now let's go back to this place to be able to get the answer in terms of an actual value, numerical value. So let's see. So thus distance PQ will now be equal to 30 times T1, which is 5, which will give you 150 meters. So this is very, very, very easy to. So that's all for that. So we have our time to be 10 seconds. So I would like you also, this is the part 1 of the VT graph. I'll give you more examples on how to solve this VT graph and we'll solve it together. So I would like you to subscribe to my channel, like, comment and share. And as you do that, you are blessed.